Start. I'm very happy to announce Juan Esteban Rodriguez Camargo, who will tell us about the Fargues-Fontaine de Rham stack.
Okay, well, thank you very much to the Francis, to Barga and Gordon for the invitation to give a talk in the seminar. So I'm going to talk about a joint work in progress with Johannes and Schutz, Guido Bosco and Arthur Cesar on this Analytic Fargues-Fontaine stack. This is also based in this. This is somehow is like a piece or a part of this mathematization project with Johannes, Arthur, and Peter Schultze. And let me maybe start this talk with just telling you what this object is supposed to capture. Maybe different from on that. So basically, the goal, well, is to construct certain object, construct a, you could say, the cohomology theory. In Analytic geometry. That captures, or such that, so that captures the following kind of objects. So something that is appears in varying works of Laurent Berger and, for example, Ketaja, Liu, and so on, is the theory of high-bound modules. In particular, there is some deviation of the theory, which is called a theory of p-adic differential equations. So this Fargues-Fontaine de Rham stack is supposed to contain that. So captures theory of p-adic differential equations. Berger. Yeah. So the symbols would make sense after, but basically this is the theory of some modules over the rubber ring with a Frobenius and with a flat connection. Okay, phi equivariant flat connections. Where they support the rubber. So this is a very important class of objects to study, for example, for things like the p-adic monology theorem, which is stated using this. The other hand, there is other kind of cohomology theories that appear, or maybe they're related by this via p-adic monodromy, which is the so-called Yoto-Kato cohomologies. And well, there are different ways to define these things, but maybe for rigid spaces, the one that we discussed to use is the one that coming from the work of Bras-Vezzani. The role is speaking, at least the way I understand is, well, the Yoto-Kato cohomology is a cohomology theory that take values in something called pi and Galois modules. That somehow improves crystalline cohomology of interruptals. So this crystalline cohomology may give you maybe some Frobenius and Galois, and this one is going to give you this nilpotent operator here. So something that refines crystalline cohomology. And these two are related via, again, p-adic monodromy. So, okay, and one are related. Yeah, p-adic monodromy theorem. Maybe the last kind of cohomology that this theory is supposed to capture is in a work of Bras and Vezzani, which is this theorem Fargues-Fontaine cohomology. after the Bras-Vezzani, which basically is a cohomology theory taking values in, for example, you map X over C, and this take values in perfect complexes of the Fargues-Fontaine curve living over C, that refines the Rham cohomology. Meaning that if you take this Fargues-Fontaine de Rham, or the Fargues-Fontaine of X over the Fargues-Fontaine curve of C, that's refining by the Bras-Vezzani using motivic methods, and you base change from this to C, you just get the usual de Rham cohomology. Right, some kind of motivic way to expand this de Rham cohomology to actually a whole perfect complex of the Fargues-Fontaine. So this Fargues-Fontaine Rham stack is supposed to capture like all these three things at the same time. Well, maybe the most appealing one is this one because it have the same name. So maybe it's going to be more direct to capture something like this, but via some kind of comparisons, you can also like encode these two at the same time. But maybe something that is very important for us is that we don't want just to construct some kind of maybe involved cohomology theory that computes these objects, but we want to have some control on the geometry of this. So this means that maybe an additional thing that we want from this theory is that this should be geometric. Or in other words, it should arise from some, or I should say, ring stack with an issue analytic stack. So in other words, the way you should construct this cohomology is by given a rigid space X, you attach a suitable stack in some sense that is going to be this the Rham Fargues-Fontaine stack. And then this cohomology is just going to be the coherent cohomology of this object. That's the goal. And well, when I say stack, I may actually mean an analytic stack in the sense of Clausen and Scholze using confidence band. Right. So to give maybe a little bit of idea of how this thing is going to supposed to look, let me continue developing this first idea of the rubber rings. Somehow I find it interesting. So for that, let me just start with the following. So let consider a power series ring in one variable, and a leaf of Frobenius. So maybe just two examples to keep in mind. We come from two leaves of Frobenius that we see in different aspects in p-adic Hodge theory. One of them is given by taking x plus 1, p minus 1, which you see this is basically just the leaf of the multiplicative law, just the multiplication of p multiplicative law. And then another one is maybe a little bit more naive. Well, a leaf of Frobenius was just given by x. Just maybe keeping these two in mind is well, actually going to be very useful. Then, well, it gives you a map like that. And then you can pass to rigid generic fibers. Which produces a map from the open unit disk of radius 1. To this guy itself. Then, well, this is a bounded function in the disk. So being a bounded function, it has just finitely many zeros, and maybe the derivative also has finitely many zeros, so maybe remark. So it's bounded. And that comes from this thing. It's implement zeros. This means that if we look at the open unit disk in the target and we restrict the map to just a curve around the boundary, here, and well, we have the Frobenius here, so here we have the same, and well, the boundary will do some crazy stuff, but do something like that. So at least the Frobenius restricted to this red piece is going to be a tau, even a finite tau, to get pretty much. Right? So at least Frobenius in general could be a little bit crazy. Like for this one has like maybe singular in roots of unit. This one is kind of singular in p-adic roots of unit. This one is singular in 0. But away these points in the boundary, these things are just like a very nice and just finite tau cover that should look pretty much the same. So some construction that people do in p-adic mesh theory is this rubber ring, which basically consists in, okay, let me just not take some fixed column, let me just take the co-limiter on all of them. So definition, the rubber ring is this thing, which is just this co-limit are going to 1 of functions in the disk of radius r to 1 here. So this ring R is endowed with a Frobenius for which it is a finite tau. So it's a reasonable map. But also, well, it basically is constructed by taking some kind of neighborhoods, some kind of global sections of smooth rigid spaces. It has an lateral connection. Actually, coming from open units. So now we can give the definition of what a p-adic differential equation is. Well, I think that's a way to define a p-adic differential equation. Definition. So the differential equation is a projective module M together with compatible Frobenius from M to M that we ask to be like with the same data, as meaning that linearized Frobenius, this is an isomorphism. So it's the usual condition you put when you want something to be like by equivariance and Frobenius to be an isomorphism. That's for these things. And this thing is just a flat connection, so basically just a flat connection. Equivariant connection. p-adic, in other words, like p-adic differential equations are just flat connections over pi equivalent flat connections over the Rover ring, which again, you should think about that basically as something close enough to having a flat connection of an open disk, except that maybe it's just defined over the boundary. But because you have the control of the Frobenius, and the Frobenius is kind of going away, then you can use this information and the fact that you have this isomorphism to spread out this differential equation. Just for example, in this second case, to something which is appointed in disk. In general, it would be like some local Fourier span, but basically you should think about this as something not too far from just being a pi equivalent flat connection in the open disk. Okay.
Sorry, isn't confused with the picture? Isn't Frobenius contracting?
Is it contracting? Yeah. Maybe. I always. Well, right, because it's just passing to the P, just comments. Thank you.
The projective R module here, should it be finitely generated?
Good question. So the answer is that actually it's going to turn out to be finite anyway.
Finitely generated. But R is
sorry, projective, yeah, finite projective.
finitely
Thank you, yes. Yes, going to be finite projective.
How far is the Roba ring from being local?
How far is the Roba ring from being local? I think it's going to be pretty much a local ring. Like somehow this kind of functions in some kind of seal-off boundary of the compactification of the disk. It's not
So this ends up being free.
Yeah, all these things turn out to be free, but maybe for that you need the Frobenius. I don't know. Yes, and if you have the Frobenius, you certainly have something that is going to be free. Right. So let me maybe use the second one, which maybe is the one that is easier to draw. So, right, let me just change a little bit for that. So, yeah, we have these differential equations, but there are other kinds of constructions we can do for this, at least, what is it? The Frobenius with this in this power series ring. So there are other funny constructions we can perform here. So one of them is the following. So consider A to be the colimit along Frobenius, this power series ring. And then you can take coefficients along P and X. So this thing, up to change the variable, this is actually isomorphic to just a power series ring in some variable TP1 infinity. And you can make a specific variable if you want via the formula used with tilting, which is some kind of limit. And I hope I don't mess up this thing. I think it's Frobenius minus n to the x, like the one coming from this node, and then you write this to the P2n. Like you look at this formula, and this formula is going to converge in some element here that is going to have a bit power roots here.
So you mean for any phi, like for any
For any phi, yes, it doesn't matter which one. So this ring is also you describe basically as the v vectors of just fp mod tv1 infinity. And if you want, the point is that because Frobenius is just a leaf, phi is just a leaf of Frobenius, this perfection of the collinear of Frobenius, when you complete, this is just the same as taking the v vectors of the perfection mod p, and the perfection mod p completion is just this power series ring. Yes, so this kind of representation is full of flat. But I think so.
So how much does this category of p-adic differential equations depend on the Frobenius lengths?
That's a good question. Let me go to that in a second. I go to that in a second. So it's independent of the Frobenius, but somehow it's not trivial for this definition. It turns out to be independent. I hope we're going to give you a justification of independence. Oh. All right. So, maybe let's use the second set of coordinates. So maybe just example with this. Just take the Frobenius of x to be x to the p. So in this case, the variable t and the variable x is just the same. So you look at this formula is already that. And then if you take the analytic spectrum, so just the adic spectrum of the ring A, and you take the locus, you remove the locus where this t is 0, then you basically just invert t analytic in this locus. Then, this is maybe just let me invert the locus when t or p are 0. Yes, so I want to invert t and invert p. So this is something that we can write in maybe more terms, which is just this y construction, this y Fargues-Fontaine curve for this perfectoid algebra. Here, basically the definition is that. But this A has maps by construction, is just infinity to just the perfected version of this ring, which is just by adding rules of that. So this means that this guy has maps to open disks, maybe after you remove t and p. So basically you have to remove 0 because we're taking this specific case of Frobenius. And then you can just perfect by rising to the p. Right? And for this limit, let me not say exactly how to get this limit, but basically it's telling you that you have the map from this Fargues-Fontaine cube of FP of this perfectoid field towards this limit along just rising to the p. So in general, for a general Frobenius, maybe some feature of that is that this is an isomorphism on underlying. Well, basically, it gives rise an isomorphism in diamonds. Gives rise. So in other words, like after taking completions of this object, from completion, then you just get this cubic here, which basically is just the same reason why this A is just a coordinate of this thing. Same distinction. For general Frobenius, the thing that you will get is maybe you have a map from this guy. Well, you still have a map from this to this open unit disks along Frobenius. And maybe in order to make an isomorphism of diamonds, what you need to remove is kind of the fixed points of Frobenius. And this one is going to really give rise. Right. In this case, the fixed points consist on the just 0 by just the way you define. In this case, the fixed points of this thing is going to be not p power roots of unit, but just the sequence of 1, 1, 1, 1, 1, 1 in the roots of unit. So the only thing that when right to the power of 1 is just going to be 1. And in general, it's going to be maybe something more involved. But nonetheless, it's going to be these fixed points. All right. So let's go back to this. So we have this category of p-adic differential equations. and going to be the rover replicating on this Frobenius. And well, maybe in the case where Frobenius is literally just rising to the p, is maybe not going, and at least is true, but it's not too crazy that this p-adic differential equations is just a vector bundle with flat connection here should coincide with basically vector bundle with flat connection in here after maybe removing some kind of fixed points, this Frobenius. So in the maybe example that is more clear is that if you are in this case, like whenever you have a vector bundle in the rubber ring, you can this vector bundle just extended maybe all the pointed unit disk by using the Frobenius, and then because the flat connection arises from, well, literally just the connection coming from the unit disk, then you will construct a structure of a module with flat connection over the pointed unit disk. And let me maybe say that in general, you might need to take this perfection and take this Frobenius floating apart. So these things can be seen more geometrically as vector bundles over this kind of limit. But again, this limit you can think just as taking basically co-limits of these functions. Flat connection. This can try to make sense of this, just talking with the theory of real spaces. But somehow all these spaces have the feature that their completion agree with this Fargues-Fontaine curve. So you will really like to say that, okay, this should be just nothing but vector bundle with flat connection on this Fargues-Fontaine curve. Question mark is maybe how. Why? And again, like the way people deal with rubber rings and the geometric intuition behind is always try to think about that. That somehow you have this Fargues-Fontaine curve, you can kind of construct a decompletion of that, which in this case means this specific presentation, and maybe after some kind of reductions, you can just like build up everything just from a module over the rubber ring with enough structure, just by again spreading out the Frobenius way. But of course, this thing on the nose doesn't make sense. This thing. Like that. Good sense. Classically. And the reason is because if you look at the differentials of the Fargues-Fontaine curve over QP, well, you just get 0. And even if you look at the cotangent complex of this thing of the Fargues-Fontaine curve, you just get 0. So there is no way that a traditional theory of D modules or vector bundle flat connection is going to solve this question. But let me highlight that if this were true using these maps, then this will answer the question, because then, well, these things are just the same as these things, and the same as these things, and this one is completely independent of Frobenius. So this Fargues-Fontaine de Rham stack, just erase the title, is supposed to give you a way to talk about the vector bundle with flat connection in a good sense here, such that this becomes true. So even though you don't have differentials, you can still talk about D modules in a pseudo sense.
But I'm confused. So the last category, is it vector bundles on Y or Y divided by Frobenius?
You're totally right. I really wanted to do vector Frobenius. Thank you. Thank you, thank you, thank you. Yes. This one as well. Right? Because of the Frobenius and the rubber ring. One to the other. Yes, thank you very much. So in order to make this well, kind of strange claim and data realized, I need to talk about something before the analytic or the Fargues-Fontaine stack, which is this analytic Rham stacks. And maybe want to spend enough time with this, hopefully not too much. But basically, kind of the idea is to build up or construct the good theory of d-modules of p-adic geometry. Well, maybe the one idea, but maybe that relates with something that you may call as infinite order. P-adic differential operators. So this is something that may come from complex analysis. Is like you can define a sheaf of infinite order differential operators, which is just the endomorphisms of the structural sheaf over the complex numbers or the real numbers, for a smooth manifold or for a complex analytic manifold. So there is something you can do in the p-adics, which is not exactly that, but that is the analog of this sheaf, which is something that called T-cup, and that was introduced by Atakov. So in classical algebraic geometry, well, you have the theory of d-modules, compute one cohomology, and encode vector bundles with flat connections as d-modules which are coherent or modules. And the theory of d-modules in algebraic geometry actually came from geometry itself by Simpson's construction of this algebraic theorem stack, where these things came from. And the idea is that there should be some kind of analog construction in analytic geometry that somehow should encode this theory instead, as opposed to just algebraic models. And should have changed this. And well, maybe I'm just going to say it loud, but in Simpson's approach, it's kind of inspired from Grothendieck's perspective of the way you think about a vector bundle with flat connection using just thickenings of the diagonal. So in this case, we are going to also use the kind of the diagonal to build up a stack that knows about that, but it's just a different way to think about the diagonal. So let me maybe just start with some example. So let's take X be maybe classically a scheme over C. Let me say smooth. Then the algebraic theorem stack of Simpson of X, you can compute it. It's not a definition, but you can compute it as taking the scheme X, and then you just mod out by some equivalence relation. Is given by the formal completion of the diagonal, which lives in this plot here. So it turns out that quasi-coherent sheaves will be stacked, which is algebraic, just some functor of points, the functor of rings is the same as d modules over H itself. That's a construction of Simpson. So in p-adic geometry, if you take X to be a smooth Ridge space, then this analytic theorem stack is going to have a very similar shape as the algebraic theorem stack, There's going to be a quotient of x by some kind of equivalence relation. But this time, this equivalence relation is something slightly different. So as opposed to taking the formal completion, which is just an int scheme on the product of two copies of x, we are going to take something that if you think about what looks in rigid spaces, is basically just taking the intersection of all open neighborhoods of the diagonal, which means some kind of overconvergent neighborhood. Of the diagonal. Right, so in rigid geometry, whenever we're in complex geometry, we also have a new feature is that you can, given a space, you cannot just talk about functions with basically just a infinitesimally deformed space, but also you can talk about functions which overconverge around the space. So again, this one is just a topological space if you want, given by x, but the sheaf of functions is the function just given by these overconvergent functions in the diagonal. So again, this is more than a definition, it's a computation. And in this case, this analytic Rham stack is going to be related with the Camargo. So in this case, to say this, quasi-coherent sheaf of this thing is going to be related in a specific sense with the like there is more precise study, but just to maybe keep in mind like the analogy here. But for this thing, this algebras have to be useful in this like point of view for the differential equations. You actually need to go a little bit more fancy than that construction. So for that, maybe let me just state yeah, let me give a provisional definition of this thing that actually is just equivalent stack. So as I said, these objects live in this world of analytic geometry. So let me start with some categories of solving the algebras, kind of completed algebras for the product of some kind of p-adic tensor products. Inside this category, well, you have just Banach algebras. Banach algebras. State algebras, perfectoid rings, and so on. And well, this category has all colimits. So, Banach rings. This category has all colimits. So something you can do is just take the smallest category here containing this one that is stable under colimits. And let me call these bounded rings. This one is the smallest category. Meaning rings. It means yes, it means unusual Banach ring. I mean, this one is a bit larger, but it's not far from that usual Banach ring. I mean, the green, yeah, in this one we just use a Banach ring. It's just a ring whose underlying topological space is a Banach ring, or condensed set. And stable. Under colimits. Okay, so why this category is useful? Well, already contains Banach rings and maybe all data algebras that we know they are basically Banach rings by definition. But more important is that within this category, I can now start talking about these overconvergent functions in a precise sense. examples. Of course, one is just a thing here for a opaque algebra, the algebra, but also QP the dagger, which is just the function that overconverge at the disk of radius 1. So we think that 0. P of PRP. It's just a co-limit of Banach algebras. So it's inside this category. But another one that also sits in this category is some important algebra. Let me call it QP with some kind of fancy brackets, which is just the function that overconverges one point. Right? These two give you maybe non-trivial examples of things that are co-limits of Banach rings, which are not necessarily Banach rings, like this guy is here. And in particular, like whenever you have an affinoid here, these functions that overconverge kind of affinoid neighborhood, they're going to be just co-limits of Banach algebras. Just by the way they are defined here, just co-limits of these guys. So inside this category, so given an object, which is just a co-limit of Banach algebras, I can define the different objects. So first, I can define some kind of elements of norm less than or equal to 1, which you should think about the elements of functions of spectral norm less than or equal to 1. Think about just the like operators of clear star algebra. It's kind of the things you should be thinking about. And this one, well, at least at the level of points, you can define it as maps of rings. Well, you basically just need to model these objects by what is the condition to be of norm less than 1. And this is precisely what this less than or equal to 1 is, this overconvergent algebra is capturing. It's like something has norm less than or equal to 1 is basically as this function, like however you say, can be kind of, so if the plural algebra can be completed to this more overconvergent function. So this is definition motivated from just a universal case, which is this overconvergent Banach algebra, overconvergent algebra. It turns out that gives you a very reasonable definition. These are the good ones here. There are elements of a spectral norm 0, something that we call this new one. So basically, elements of spectral norm 0, which you can write at the intersection of, well, P to the n of guys, but also you can just write it down as, again, the thing that I wrote this funny ring here. Like something is going to have norm 0, it basically we divide by P and it's going to be 1. So this thing is going to be. So given these two constructions, there are a couple of contours you can define in these algebras that well, these appear everywhere whenever you do p-adic geometry. I mean, even one of them already appears when you do some kind of sister algebras, maybe here, and this one, this construction from here is something that appears in geometry. So given some algebra here, kind of bounded algebra, co-limit of Banach algebras, I can define the reduction of the algebra, which is given by killing the elements of norm zero. So basically, it's kind of it's not like the completion for the spectral norm, but at least in killing the kernel of the spectral norm. So any element in here, which is, if it has a spectral norm zero, actually is going to be zero. This is the part that we just kill this guy. And the other one is maybe actually the completion for the spectral norm, which is the uniform completion of A, which is given by taking this, taking the p-adic completion, and then just integrate. So again, like maybe these are constructions that are these kind of not let's say natural when you some analysis over algebras, and maybe you can extend more over some co-limits. This is the way you extend it on co-limits algebras. And then using this construction is how you can define this Rham stack. So definition. So let x be.
What kind of objects are these?
Yes.
And what kind of objects are these?
These are still objects in here. And this one is even a Banach algebra. Yeah, this one is, well, yeah, more or less going to be a Banach algebra in some sense. And this one is just an object in these categories. Can be very, very, maybe let me just do an example of these constructions. And maybe, well, if A is a theta algebra of finite type, then the uniform completion is the same as the reduction, which is the same as the actual reduction. Meaning that the only elements of norm zero are precisely the nilpotent elements of the theta algebra, some kind of classical theorem with geometry, and the theta algebra, which has no nilpotents, is already uniformly complete. So in this case, like these three things just coincide and give you the same answer. Maybe for the other example, take A to be this overconvergent thing. So the reduction of A is just itself, because like any function here is going to have norm zero, because kind of the universal variable have norm one by the way we construct it. But the uniform completion of this guy is just the theta algebra in one variable, like the Banach algebra is. So in this case, the three are actually different. Well, actually, the first two are equivalent, and the uniform completion is different. And maybe another example, which is with this funny algebra at the end, is overconverging functions at zero. Well, in this case, the reduction will coincide with the uniform completion, and because the variable and anything that is divisible by the variable has a spectral norm zero, sort of by construction of this algebra, this is just given by QP. So these are kind of two different constructions that captures different features of like co-limits of Banach rings depending on the kind of co-limit you look at. The three of them are actually great. So let me state the definition and maybe just a working example theorem of this analytic Rham stack. So definition. Let's say X is the analytic space. Can just make the definition more general for analytic stacks. Then it's analytic Rham stack. This and maybe the code specification of, let's say, for the topology of analytic stacks. I want to talk about this. Of the contour. It's the Rham analytic coming from this bounded algebras to sets. Well, in this case, it's just a usual classic static space, so it's not going to be much difference. It was here that takes an algebra and maps to the reduction, which is again the same definition that or at least the analog definition that you will get from Simpson. You have algebras and the Rham stack. The algebraic one is just taking the R value of X Rham is just X in the reduction, the algebraic reduction of X itself. This one I told you that you actually need to take this kind of spectral reduction. Then theorem. Still have how much time do you still have?
9 minutes.
9 minutes. Okay. And so I give you the definition. Now let me give you a theorem. With maybe star, meaning that is still not written, which tells you the way you can compute the Rham stacks, maybe using these operations. Like we already saw that for rigid spaces is just given by this quotient, by this overconverging diagonal, and the category of quasi-coherent sheaf is kind of explicit using Dika modules, kind of D-model theory that can be explicitly written. And then the idea is that, well, we know that only computation for rigid spaces, and we want just to understand everything else from that. So this is what this theorem is going to tell you. So let A be bounded. And well, suppose it is, well, this is just a provisional name, and maybe just put in quotes, so separable. So the idea is that the unit for completion is separable Mach space. Meaning that it has a countable orthonormal basis as a Banach algebra, as a Banach space. So you should put it into Banach space. That's some kind of, well, you can think about some kind of topological condition, even though it's more like an algebraic condition. Then, if you take the analytic spectrum, which again is just a spectrum in this world of analytic geometry of transformation sources, so that the Rham stack attached to this thing that can be like more general, let's say, than just having spaces there. This is just the same as the Rham stack. Of the uniform completion, these guys. So, in other words, it tells you that this process to pass to this analytic Rham stack, it somehow they complete your rings sort of for free. In this explicit sense, like the passes to the Rham stack is independent of uniform completions. So it's actually very powerful. So, well, there are other theorems, so let me maybe just say that loud and explicit is that like this is kind of important.
So is this probability equivalent to like Aleph-1 compact in some category?
Aleph-1 compact in some category.
Aleph-1 compactness of A.
I can tell you what this translates to. That works. It basically tells you that. Let me maybe just start it off. It says that any variable on the ring A has a descendable over AB such that B reduced the same as the uniform and even perfected. So it translates to this statement. I mean, this is kind of the thing you actually end up proving, and somehow it's going to imply this. It's more about something being descendable.
What's the
That this one is perfected.
Even in the English sense.
Even in the English sense.
You mean this separability implies there is such a cohort, not that this is.
Yes, the separability will imply this thing.
okay, so maybe it's more basic question. So do we have natural maps from A to A reduction to AU?
Yes. That's a very good point. Yes. Thank you. So we have a map from this to this to this, and I think this one is even an injection. Yes. Thank you. It's a good one.
Right, so so it would be enough to have these ascendable covers. You don't need the countability.
Right. The point is that I only know how to produce these things under the countability as well, because of usual things that flat maps are kind of descendable.
Like if your index category has some like finite convolutional dimension, it should be.
Right. That should be enough. Yes. Yeah, this case is more like just for. I mean, as I say, this one looks like an analytic reason, but actually the reason is algebraic. Something funny. So maybe some other remark is that actually, like even, I don't know, like if you have a map perfect with rings, maybe this one, the key limit of ANs is completed with A to AN being some kind of italic cover. So basically just kind of proetal map, or maybe countable proetal map. And I'm just ignoring the A plus, just underline rings. Then you can prove that the dispatch to maybe this should be more than a remark, like a second part of the theorem. Sorry about that. Is that this thing from E the Rham to this guy? Rham is actually an epimorphism. I mean, you can even say that it's like a very nice epimorphism, but in particular, it's an epimorphism. So this just translates. So this second part of the theorem translates to the Rham stack, or the Rham stack satisfies, or not all, but let me just say the total descent. In particular, this is well defined for diamonds, so it's going to be like well defined values.
But so dealing for some kind of diamonds or
Well, diamonds that maybe are like quotients by countable limits of prototype equivalence relations.
Okay.
So this is like for all diamonds you will encounter that. This is the story.
so is it expected that it just depends on the diamond or is it
Let's say that the problem for these kind of things is just because sometimes, I mean, it's kind of the same problem that arbitrary flat maps are not descendable. At least kind of the same spirit. Not the same, but the same spirit. And this topology of analytic stack is actually kind of uses the descendable point of view instead of the flat point of view. So it's kind of this same sort of abstraction of that. Yeah, sorry, someone to ask one your last question.
So it's slightly weaker than usual prototype.
So yeah, it's slightly we're gonna use a prototype, but it's more than enough for rigid geometry. Fortunately,
so far?
so far. I mean, it's a little bit annoying, but at least it's so far. Okay, so we have all these fancy constructions. Well, this kind of nice theorem told you that there exists a kind of object for which you can construct from Rham stack, and you have this kind of the completion of the Rham stacks that you can descend to diamonds using this property theorem. So let's go back to the rubber ring. I'm going to finish that. So recall that we've had a map from this y of fp over parentheses t 1 over p infinity going to the limit around Frobenius of these open disks, one of these fixed points. And then the invariance on the order from completion we told you that actually when you take analytic Rham stacks, these two things are the same. And well, they simply define properly, you can even just take this one aside. Maybe we just so this one is at least up before sheavification, it's just the same as taking like the Rham stack of these ones. And then you just remove the fixed points. So those are what we actually wanted before, like maybe before multiple Frobenius was even better because we didn't Frobenius is that like the theorem of p-adic differential equations, which was completely rubber ring and maybe extended here is in the Frobenius, is something that is completely independent of the Frobenius and the coordinate you choose, because it's just the same as vector bundles in this funny object in here. So as I said, like this thing is something that can be constructed for diamonds. In particular, you can take X to be a real space. Let's say over C. Then this guy has a diamond over SPD of C, and diamonds they have attached some kind of this using the descent. You can just define a stack attached to this diamond that is going to live directly over the stack attached to this guy, that in particular has a map from here, sorry, from the curve itself. So you can define some kind of relative to Rham stack here over Y of C. And this guy, well, this is the expectation. Kind of the theory is built up this way. Is that the cohomology, which is always displayed here, of just the structural sheaf of this thing should be as Bras-Vezzani is Fargues-Fontaine de Rham cohomology or the Fargues-Fontaine cohomology, which together was defined like using completely different means, using like more like motivic approximations and approximated motives from X to the tilt and playing around with these things. But here it just gives you like a well, kind of sort of explicit way to talk about that, at least explicit as analytic stacks are. I think it's already kind of time. So yeah, it's going to finish. Thank you very much for.
Any questions to the speaker?
So what is the descent code?
In this?
Yeah.
That's a good question. So in this case, the descent is also going to be just the overcomparative diagonal of this guy. Which is a little bit strange.
So but there's no like concrete meaning for that extra structure on the broad part?
I will say that directly from this one is not. It's not that I can literally just see them. It's going to be some descent data. Maybe it's going to be a descent data and you can make out from an abelian category itself. But it's as explicit that this overconvergent diagonal is going to give you a descent data, which maybe it's not much, unfortunately. Right. So this is the funny part. Like somehow some descent data are a little bit mysterious. So the one that is less mysterious, or maybe not like not obvious, but for really spaces, that's the same data can be actually compared with some kind of TLT models. So this one itself maybe cannot be captured with a TLT models, but you can then complete this space, for example, by taking, I don't know, this kind of limit by Frobenius ectopico. And for this the completion, you still have the same theorem stack. And now the descent data you get from these decompletions are actually linked with the honest theory of the models in something close enough to real spaces. So always kind of depend on what you start with. You make it something reasonable or just some kind of abstract descent that for 6 pointers is good, but maybe not for explicit descriptions of this here. But for example, something that is very useful this map, as opposed from these decompletions, is that like in the proof of the p-adic mononomial theorem, like one of the key parts that Keladia did is construct a theory of a slope theory for 5 modules with connections on this rubber ring. And somehow you already have access to this using the curve. So one of the key aspects is that like, the Harvard and Riemann filtration is stable under the differential operator. And this is something you can just prove, for example, using this descent point of view here. So cannot display it, but it's very useful for some abstract.
I have the same question as before, so just to construct the Fargues-Fontaine de Rham, are you using y, not y modulo?
I want to use y. I want to use y because y is the one that commutes with fiber products.
So a priori, this cohomology you constructed, it doesn't come with it.
It does, I mean, the cohomology differential sheaf it does, because it's just the pullback of the quotient by Frobenius. But if you start with an abstract vector bundling here, it does not. You actually will need to model with Frobenius. But the structural sheaf itself is not a problem, right? Because I mean, for that, the only thing you need to do is just take. I mean, this one has a natural Frobenius, so you just need to do this, which is also just something kind of a quotient at project space. Just,
Any other questions from the speaker?
Okay, no questions. Let's thank the speaker again.